Thank you.
Mommy.
Thank you. All right. So I included on the original note sheet 4.1a, I had included this information and I kept it on this note sheet as well. So it's still the same information, but I just wanted to remind all of you about it. So related rates problems. The whole idea behind these is you're computing the rate of change of one quantity in terms of the rate of change of something else, which might be more easily measured. So you want to find an equation that relates the two quantities that you have in your problem and use implicit differentiation, which is an application of the chain rule, to differentiate both sides. And everything is differentiated with respect to time. So you're taking d dt, or the derivative with respect to time of everything, and that's where the implicit differentiation, the chain rule, comes in. So for the first example I have on here, so this is reviewing the overall process, and then there's also, well, there's just some little things that could come up within the examples that I had picked these two for a reason. So example 1 says a water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. So you're always asked, and you can see in this problem, I'm just going to highlight what we're finding. So you're always going to be asked to find a rate at some condition. So in this case, the rate at which the water level is rising when the water is 3 meters deep. And we're going to be assigning variables to all of this and trying to piece together what we have first before we find any derivatives, anything like that. So I left space. For some problems, it's helpful if you have some sort of diagram to look at. So here, because it's talking about an inverted circular cone, so just a circular cone that's on its tip, if you will. So you say it feels like Thursday?
Yeah.
Okay, so an inverted circular cone. And like I said, too, for these, so some of the problems that you'll have here, any formulas for the relationships you might need, you might be thinking, oh, am I expected to remember that from geometry? No. So a lot of formulas they may not be given to you in the practice in here when it actually comes to AP questions or questions I would give you on a quiz or test. If there's some formula like the surface area of a sphere, do I expect you to remember that? No, that would be provided to you. So it might not be provided right here on this, but at least with homework and things like that, you have the opportunity to look it up. On a test or quiz, I'm not expecting that you have all of those memorized from geometry. So we have the inverted circular cone. It has a base radius of 2 meters. So the base would actually be this circle. So this radius up here is 2. And then the height of the entire thing is 4 meters. I'm just labeling what I know. And then it says if water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. So we have water being pumped into the tank, and I'm just going to draw it at a random place. So say it ends up at, it's here for right now, so this would all be filled with water. Okay. So we have to assign variables and everything to this to figure out what we have in terms of rates, what we need to find. We have no variables listed right now. So first of all, if water is being pumped into this tank, it might be helpful in this situation to kind of think of the relationship or what formula you're trying to work with here. Anybody know when it's giving us the rate that it's being pumped into the tank at 2 meters cubed per minute, what that would be the rate of? The rate of, yeah, the change of the volume. So we're talking about the volume of a circular cone. So this is the case. Does anybody remember that formula from geometry? Okay, Dalton does. So would you be expected to just know this? No. 1/3 pi r squared h. Okay, so we are talking about the volume of the water in this circular cone. So this is going to be our relationship here. So we are given then the rate of the volume. So the dV dt rate of the volume with respect to time is the 2 meters cubed per minute. So I'm just going to say this equals 2. And then we're trying to find the rate at which the water level is rising when the water is 3 meters deep. So what are we trying to find the rate of in terms of variables here? The rate of h of the height. So the water level rising, the water level would be the height. So we're trying to find dh dt when the water is 3 meters deep. So yeah, when h is 3. Okay, so this to me is the most difficult part of these problems. Just knowing what to set up, because you can't obviously find the derivative of something if you're not even sure what any of this is. So before we go through and find the derivative, things like that, are there questions just on this setup? And I know every problem's different, so it doesn't mean just because I'm showing you this that everyone's going to be set up the same way. That is the toughest part of these. Okay, so then working through this, one thing with this one, I included this example for a specific reason because notice the relationship for the volume of a circular cone. The volume is in terms of the radius and the height. However, we have the rate of volume. We're trying to find the rate of the height. We have no information about the rate of the radius. So because of that, before I actually find the derivative of this, I want to express the volume just in terms of the height. I want to get rid of my variable r so that I have v just in terms of h. I'm just going to make a note, express in terms of h only. So if you have a problem like that, and we would have found this out too, if I find the derivative, I'm going to have dr dt somewhere in there, and I have no information about that. And that's a clue that we should be able to get rid of it somehow. But that would come before you actually take the derivative, is get rid of the r. So what I have to do is I have to substitute something in for r. I need to figure out an expression for the radius in terms of the height. So here's how to do that. And again, this problem is maybe more challenging for coming up with this. Some problems like this, it might be substituting diameter in for the radius, and that the relationship between a diameter and radius is easier, in my opinion, than trying to figure out this relationship here. So if I were at any random point within this cone, so let's say this circle here, so this radius of this circle would be changing. I'm just going to call that r. And the height of the water at that point is also changing. I'm just going to call that h. So what I can do here is I can set up a proportion, because I know the maximum radius, the maximum height, and then I know the radius at any point is r, the height at any point is h. So I can say the radius is to the height as 2 is to 4. Just setting up a proportion. Okay, and then I know 2/4 is 1/2, and if I multiply the h over, this means the radius at any water level here, the radius is half of the height. And you could maybe even see that from the maximum radius and height, the radius is exactly half. So I can then replace this r in my volume formula with 1/2 h. and then volume will just be in terms of h. So I would have V equals 1/3 pi times the quantity 1/2 h squared times h. So then here I know the 1/2 squared is going to be 1/4, and if I multiply that by 1/3, I'll have 1/12. I'll still have pi, and then I'll have h squared times h, so I'll have h cubed. But now I have the volume just in terms of h. Okay, so again, do you always need to do this? No, it's just if you see there's a variable that you have no information for the rate of. You always need something to substitute in there. So then, now I'm at the point where I can take the derivative of everything with respect to time. So I'm taking d dt of everything on both sides. So the derivative with respect to time of v is just going to be dv dt, or I could think the derivative of v is 1 and then multiplied by dv dt. So it's that implicit differentiation because you're with respect to t. You're confused?
Yeah, I don't know.
Where all the d's are coming from?
Yeah, like.
Well, this means ddt is just my way of saying I'm taking the derivative of everything with respect to t.
Oh, okay.
And then this is actually this is like v prime of t, is what this means. Okay. And then over here, the derivative of 1/12 pi h cubed. So I'm really just taking the derivative of h cubed. The 1/2 pi is the coefficient. So I multiply the 3 by 1/12, that's 1/4. Keep the pi, and then it's h squared. But then I have to multiply by dh dt. So it's implicit differentiation. So it's kind of like when you use implicit differentiation, anytime you took the derivative of y, you had to multiply by dy dx. This is the same reason because you're taking the derivative with respect to a different variable. That's why. Okay, before I move on, any other questions? Please keep asking if you have questions on something. So then, now you're at the point where you should be able to substitute a number in for everything except for what you're trying to find, which in this case is dh dt. You don't, because 1/12 pi is just a coefficient. Right, but this is just a coefficient, so if you did a product rule, like if you said this is your first, this is your second, with the product rule, the derivative of your first is just 0, because it's a coefficient. So you don't need the product rule. You only need the product rule if you're multiplying two variables together. I mean, could you use the product rule? Yes, you just don't need it because it's a coefficient. So then dv dt, so now we go back to what we were given. dv dt we know is 2 equals 1/4 pi times, we are finding dh dt when h is 3, so we substitute 3 in for the h, and then we don't know dh dt, but we can now solve this equation for it. Okay, so I'm just going to simplify the right side here. So 2 equals 3 squared is 9. So I would have, I'm going to write this as 9 pi fourths dh dt, because then to solve for dh dt, I can multiply by the reciprocal. I can multiply by 4/9 pi. So that'll cancel out. So then dh dt will equal, this is like 2/1, so it'll equal 8/9 pi. So that would be the exact, which you could leave it as exact, or if you gave a decimal answer, you would round it to how many decimal places? 3. And then be careful too, if you are, I don't have my graphing calculator out here, but if you are dividing this, do not just type in 8 divided by 9 pi. You will not get the right answer because you want the 9 pi multiplied first. Your calculator here is going to divide and then multiply. So you would need to type it in as 8 divided by the quantity 9 pi. So it would be about 283, 0.283. And then what would the units be on the dH/dt? I heard per minute. Meters per minute. Height is measured in meters. Okay, so overall process, if you're not given a diagram and it helps you to draw one, draw a diagram, figure out what are you given, what is it you're trying to find. There's always a condition. What's the relationship? Take the derivative and you should be able to substitute a value in for everything except for what you're trying to find. Okay, so I have another example that is a completely different setup. So example 2 says a man walks along a straight path at a speed of 4 feet per second, and a searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay. Read through it. Then this, I would think the same thing. Read through this. What? So I would draw some diagram. I want to see what's going on. So I'm going to go back. A man walks along a straight path at a speed of 4 feet per second. So I'm not going to draw a man, but say this is the path he's walking along. Okay. Now again, I've said in a diagram, anything that would be changing length, you should assign a variable to it. So I know this is going to be a side of something. So I'm going to just call this x because I know that it's changing. The length of that is changing based on how far he's walking. Okay? And I'm labeling it x because then I'm given the man's speed is 4 feet per second. So I'm given the rate of x in the problem. So then it says a searchlight is located on the ground 20 feet from the path and is kept focused on the man. So wherever I'm just going to draw, say the searchlight is here. This is the light. And say at some point the man is here. I don't know how detailed you want to get with your drawing. So the searchlight is kept focused on the man. So as he moves, the searchlight's following him. At what rate is the searchlight rotating when the man is 15 feet from the point on the path that's closest to the searchlight? Okay, so I'm just going to draw the light is focused on the man. So I have the path of the light. And then when it talks about the man being 15 feet from the point on the path closest to the searchlight, it would be the what? So the searchlight is 20 feet from the path, yes, and the closest distance would be the distance that's perpendicular. That would be the 20. So the light is 20 feet from the path. The point on the path that's the closest distance to the light would make a perpendicular to the light. So then we can decide later when we're writing what we're trying to find what that 15 feet actually is. But we're ultimately looking for at what rate is the searchlight rotating, which is an angle. Okay, so you can call the angle what you want. I'm going to use theta. If you don't like theta, you want to use a variable, that's fine. You just have to label what it is. Okay, so then what we are given. The man walks along a straight path at a speed of 4 feet per second. So I have the path he's walking labeled as x. So that means dx dt is 4. Okay, and then I already have searchlight is located on the ground 20 feet from the path and is kept focused on the man. So this side of this triangle I drew, this side is constant. That remains 20. This side is changing length. We'll see if we need that, because we could say this is y, because it is changing length. At what rate is the searchlight rotating? So we're looking for the change of theta with respect to time. When the man is 15 feet from the point on the path closest to the searchlight. So we're finding d theta dt when what equals 15? X, when x is 15. Okay, so notice I labeled y on my diagram, but I don't need y for anything here. So it's fine if I don't have dy dt. I just want to make sure when I come up with a relationship that my relationship doesn't include y. Because I don't have dy dt, and I don't need it for anything. So looking at the diagram you drew, what's the relationship, or what is a relationship between theta and x? Something with sine, cosine. Say that again. Okay, so we have a right triangle here. X is the opposite of theta. 20 is adjacent to theta. Opposite over adjacent is tangent. So when you have related rates problems that are looking for the rate of an angle, your relationship is going to be a trig function. You just have to figure out which one to use. And you could also use reciprocal trig functions as well. Okay, before then I take the derivative of this, one thing I would probably do is just multiply 20 on each side. You could call this 1/20th x. I'm just going to multiply 20 on each side. And I'm going to flip it around, so x is equal to 20 times tangent of theta. Okay, and again, nothing is plugged in until after you've taken the derivative. So now I want to take the derivative with respect to time of everything. So derivative with respect to time of x is dx dt, or 1 times dx dt, equals, the 20 is a coefficient, so the 20 will stay. Derivative of tangent of theta, secant squared theta times d theta dt. Okay? That's the derivative. You plug in, you should be able to plug in something for everything, except for, in this case, d theta dt. So we know dx dt is 4. We have the 20. We don't know theta, so we don't know secant squared of theta, but we can find it. Okay? So, remember secant squared of theta, I'm just going to do this off to the side here. So secant squared of theta is just secant of theta squared. So you don't even need to find what theta is, you just need to find secant of theta. So what is the ratio for secant of theta? It's 1 over cosine. Yes, so because cosine of theta is adjacent over hypotenuse, secant of theta is the reciprocal, hypotenuse over adjacent. So the hypotenuse is y, and the adjacent is 20. So we have secant of theta squared is going to be y over 20 squared, but we don't know y. Yes, so now how do you find y? Yes, Pythagorean theorem, because you know x is 15, and you know this side's 20. Yes, it's 25. So yes, so it'd be, yes, 15 squared plus 20 squared equals y squared. Yeah, this ends up being 625, so y is 25. So then, going back up to here, so then secant of theta squared is really 25 over 20 squared, which then 25 over 20, you can simplify to 5/4. And 5/4 squared would be 25/16. So in place of secant squared theta, I can substitute in 25/16. And now I have what I need that I can solve for d theta dt. So I would even simplify further. Here this is 20 over 1, so here I could simplify the 20 and the 16 to be 5/4. So that'd be 4 equals 125/4 times d theta dt. So that I can multiply by 4 over 125 to solve for d theta dt. So the exact answer would be 16/125 or 0.128. Thank you. Okay. Either answer you give is fine. This is an exact answer itself. Units. Yeah, so theta angles in calculus are always measured in radians. So it's radians, RAD for short, radians per second. Time is measured in seconds in this problem. Yes, Dylan. Yep.